I'm happy to introduce our work on learning implicit priors for motion optimization, a joint collaboration of Technical University of Darmstadt and the University of Washington. In motion optimization, we deal with the problem of finding a trajectory tau that maximizes over a multi-objective problem. In the equation, each cost function c defines a different objective the robot needs to maximize. As shown in the video, to find a solution to the task of cleaning a table or placing a bottle in the fridge, we need to satisfy multiple objectives that are modeled as cost functions. We have to avoid collisions, consider the robot's joint limits, and of course, solve the task. Nevertheless, a lot of times some of these objectives might be hard to model or computationally very demanding, and then we usually rely on learning-based methods given some demonstrations. Learning from demonstration methods are commonly used to represent hard-to-model objectives. Given some demonstrations, representing the task we want to solve, we can fit a model that describes the distribution of this data. Then in practice, we can initialize our optimization problem sampling a trajectory from the learned demonstration that represents the task that we aim to solve, and then once we have this sampled trajectory, we can optimize to solve additional objectives, such as obstacle avoidance. Nevertheless, the state-of-the-art approaches on learning from demonstration contains a set of limitations. First, these methods are not composable. If we have multiple learned models that we aim to maximize jointly, we cannot combine them. Second, the specificity of these methods is quite limited. In the most common cases, Gaussians are used to represent the demonstration distributions that are not able to properly represent multimodal distributions. Finally, we are required to learn them in the space in which we optimize. If we are optimizing a trajectory in the robot's configuration space, we are required to learn a model in the robot's configuration space. Nevertheless, a lot of times it makes more sense to represent the motion in the task space of the robot, as it is a more meaningful space. The motivation of our work is to propose a method for learning from demonstration that fits better to the problem of motion optimization. Our work is inspired on the successful stories of the last years in image generation. Implicit models, such as energy-based models and diffusion models, have outperformed previous explicit methods, such as variational autoencoders and generative adversarial networks, with clear examples as DALI2 or stable diffusion. Our work builds on the realization that previous methods for learning from demonstrations on motion optimizations are based on explicit methods. Thus, we wonder, can we use implicit methods for motion optimization, and do they provide better properties than explicit methods? Explicit models are quite different from implicit models in motion optimization. Well, with an explicit model, you can directly generate a trajectory tau. An implicit model allows you to evaluate the probability of a trajectory, outputting a scalar energy value V. This difference provides a set of interesting properties to implicit models with respect to explicit ones. In motion optimization, explicit models are usually used as initial sampling distributions. Instead, implicit models are integrated in the motion optimization problem as an additional cost function. We visualize the learned model with the energy function E. The implicit models are composable in contrast with the explicit ones. This means that given two learned models, we can easily put them both together as factors, influencing in the motion optimization problem. In practice, we can easily combine them, adding both as cost functions, as we can visualize. Implicit models are more expressive with respect to explicit ones. As we observe in the image generation problem, implicit models have been able to represent with a higher fidelity complex data distributions. This property is important for motion optimization as we can represent more complex robot motion skills. Finally, implicit models allow us to represent the models in the task space even if we are optimizing in the joint space. This property is essential to represent complex robot behaviors. With implicit models, we can learn the decided robot skills in the task space. Then, in practice, given we have access to the forward kinematics model phi, we can evaluate the cost of a particular configuration space trajectory by first mapping it to the task space and then evaluating its costs. In our work, we propose 4 practical considerations to exploit energy-based models for motion optimization. Let me introduce them one by one. we propose modeling object-centric energy-based models. Let us assume generating Purin trajectories by motion optimization in which the Purin task is modeled by an implicit function E. Nevertheless, we would like to learn the energy function such that it can easily adapt to different Purin places. We do so by learning an energy function that is centered on the object we aim to pur, such that whenever the object is, the learned cost function will adapt to it. We also propose to model the energy-based models conditioned on the phase of the trajectory. A problem of learning energy-based models for trajectories is the dimensionality. The dimension of a robot trajectory is directly related with the number of waypoints x in which we discretize, usually leading to very high dimensional inputs. We propose learning a phase-conditioned implicit model to reduce the dimensionality of the learned space. Our energy-based model is now conditioned on the phase of the task. We additionally propose adding the noise and regularization in the training loss function to learn smoother functions, and we introduce a novel trajectory optimization approach that combines the smoothness of the Gaussian processes with the stochastic optimization methods. We show that our proposed method allows us to find trajectories given our learned model as cost functions. In our work, we exploited all the proposed elements to learn energy-based models and use them into motion optimization. We have learned an energy-based model representing the Purin task given a set of demonstrations. Then, we combine it with obstacle avoidance and join limits, cost functions, and optimize join lib. As we can observe, the learned model adapts to arbitrary positions of the target and avoids arbitrary positioned obstacles. In conclusion, we show that energy-based models are better suited for motion optimization than previous state-of-the-art approaches, and show how to adapt them. Find additional details in our paper accessible through the QR code. Thank you.